Okay, great. We will make a start. Good afternoon, everyone, and welcome to today's IUA webinar on using climate signals to navigate an uncertain hurricane season with guest speakers from Maximum Information. My name is Mel Antawi, and I'll be chairing today's session on behalf of the IUA. We're delighted to be joined today by Tom Philp and Giacomo Favaron from Maximum Info, who'll be sharing their insights on how climate signals can help insurers to navigate uncertainty during the hurricane season. Before we begin, just a couple of housekeeping points. Today's session is being held via Zoom, as you can see, and you'll be able to submit questions through the Q&A function towards the end of the session. We will aim to pick these up afterwards and we will address all questions. The session is also being recorded and will be shared with attendees following the session, as well as information about CPD accreditation. With that, I'm delighted to hand over to Tom Philp and Giacomo Favaron. Thank you both for joining us today. Over to you.
Great, thank you, May. Thanks everyone for joining today. Super interesting topic that I think a few of you will probably have heard me speak about in the past, looking at the attendee list. But one of the things I think for anybody that doesn't know my background, I've always been very much focused on the decision-making aspect of the information that we're trying to use in the reinsurance sector. My broader background, I come from a hurricane research on the science side background, came over to the industry and joined Catlin back end of 2013. So I've been here for about 13 years now and worked with various teams within Catlin. So I've worked with underwriters, claims managers, actuaries, and see quite a large decision space and lots of different types of decisions that could be informed with climate information, particularly on a near-term basis. So I think this is probably going to be slightly different to the usual seasonal prediction webinars that people give, where I'll go through the science of this season and try and arm you a bit with not only understanding the predictions for this season, but actually trying to apply that signal type thinking to any other season in the future, and understanding what actually might be driving it, what the uncertainties might be. But about halfway through, I think, this slide deck, I'm intending that we sort of flip this on its head and try to come back through the information from a decision perspective. The type of thing I'm going to go run through, I'm going to try and stay high level. Ultimately, it's probably something that should be an entire semester of a course on decision theory. But I think the basis, weirdly, from the different market participants I've worked with on it, actually, most underwriters particularly have the type of thinking already systematically in their minds, just not necessarily out on paper and out to communicate. So hopefully it should chime with a lot of people. But as May said, please just gather any questions as we're going and we can try and field them at the end. So one thing to add just before I do launch into this, while I come from a hurricane science background and then into catastrophe modeling across different teams within reinsurers, Giacomo comes from a GIS background. And joined Excel while I was there as well. But he worked on the GIS underwriting team, and he very much thinks through the problem of what are underwriters thinking through. So towards the end of this, I'm going to effectively hand off the presentation to him to think through it effectively like an underwriter might, and try and apply some information here. So hopefully you get the gist of what we're trying to jump through. Obviously, just the title there. So using climate signals to navigate an uncertain hurricane season. The overall structure I'm going to take is I'll present to you on the seasonal hurricane predictions. I'll add some complicating factors that I think often are glossed over when people are actually trying to think of applying this, at least potentially from the scientific side, because I weirdly don't think that these are glossed over when it comes to the decision-making side. And actually, I think it's some of this complicating factors that actually has led to a lot of the market still not implementing the actual predictions, even though generally they can be said to be skillful. But we'll try and get that out in the open. Once we've got the complicating factors out in the open, I'll then try and introduce this decision theoretic approach, which falls under a theory called the confidence approach, that people might be able to take and apply and then respond confidently given the uncertainty that exists. At any point, obviously, please jot down our emails and ask questions at the end, but obviously you can reach out at any time should you have anything more specific to ask. First thing that I'll start with, though, is obviously this season we are running into what is being termed a super El Nino. Won't be a surprise to anyone in London, given the heat waves we've all had to live through. Our AC in my office here is still broken, so I'm sat in a sauna. But yeah, one of the side effects I think of El Nino. Um, Now, what is in store for us this season? I think the easiest way to start is this sea surface temperature plot on the left. So here, this is just taken a few days ago, actually. This is a map of sea surface temperature anomalies. So if you just average the background sea surface temperature, the reds are effectively where the current state of the sea surface is higher than average. Blues are where it's below average. You see just the massive red patch around Peru and that sort of north western side of South America. That stretches into the Central Pacific. This ultimately is the signal for El Nino. Something I should mention, given the usual interest in anything marine from the types of people we have in the market and history as well. There is a very cool story behind this being called El Nino to start with, where since the 1600s, Peruvian fishermen have been calling this El Nino because when they would notice that the sea surface temperatures off that coast of South America would sometimes get very warm. And when they did, their fish stocks would deplete because they would be going elsewhere where nutrients are upwelling and it's cold. That would have a knock-on effect on the whole food chain and usually lead to quite obvious empty fish nets, but beyond, you would see large, widespread impacts. But interestingly, the biggest impact of this usually occurs around December. So they termed it El Nino because obviously that in Spanish translates to the Christ child. And it wasn't until the late 1800s, early 1900s that Western civilization started picking up on this and understanding it. But yeah, super interesting that it's been around since the 1600s. What you will see is those anomalies are extremely large. You can just about make out, I think, in the legend on the left that this is greater than 3 degrees C we're seeing in parts of the Central Pacific. Not all of it, but effectively, once we hit anything that's 2 degrees above the average, then we're in what is known as a very strong El Nino. This is what the media likes to call Super El Nino, just for a bit more pizzazz. But you can see the forecasts of all of the forecast models on the right-hand side here. You see the mean of the statistical ones on the green line. You see the mean of the physics-based ones, the dynamical ones in the dark red line. The physics-based ones particularly saying that we are going well beyond the threshold for a strong El Nino into more this is ultimately why the news has started calling it Super El Nino. So this, I think, is the status that we're actually in. There's a couple of things there though, with like why are we talking about El Nino if we're talking about hurricanes, right? So there's a few leaps that I've already made in my narrative. So I'm going to step back and try and unpick that a bit and make sure you go away with that information. So there's nothing massively complicated here to say, even though it probably looks it from from first pass. But what's really neat about this is, while there's a lot of information contained on this slide, it's actually very simple if we just take a few key steps through it. And ultimately, this then leads to some of the narrative of why hurricanes are important with this in mind. But if you take the top left plot to start with, what we have here are the actual circulation cells that happen between the equator and the poles on Earth. So what actually gets set up here is that generally you have very cold air around the poles, which causes a sinking pattern, and very warm air over the equator, which causes a rising pattern. And as a result, largely of those two things, you end up with these three cells. There's obviously more complication when you dive into it a little bit more, but that actually is the core reason that you end up with three cells in each hemisphere that are transporting from the equator ultimately to the poles and back. Now, aside from the north to south circulation, you actually have an equivalent type circulation around the equator going from east to west as well. This is called the Walker circulation. And in normal conditions, you'll see the bottom left plot flicking back between neutral, which I'm calling normal as well, but then La Nina and El Nino conditions. But if I focus on maybe the bottom right plot, because it's just static there, in normal conditions, this is effectively the bottom right plot shows the cell that exists above the Pacific Ocean only, whereas the one on the bottom left shows the entire Earth. But usually you have a warm pool in the West Pacific where you have convection and then effectively subsidence around South America. Then you have air flowing back across the equator from east to west. In El Nino, though, what happens is you get these westerly wind bursts, and that center of convection shifts from the West Pacific into the central or even East Pacific during a warm during an El Nino year, a strong El Nino. And ultimately, you'll have seen from the previous plot, what's really happening there is it's just that shift in temperature. So the cloud and that convection is following where the warmest sea surface temperatures are. So obviously, as you saw from the satellite imagery, at the moment, those clouds are shifting over towards South America, so away from where they exist in the normal conditions. Now that, while it seems like a relatively isolated case, what actually happens to the Walker circulation worldwide is that all of those cells start to shift. And with all of those cells shifting, you have energy and water transport moving around the world. And this is what starts to drive local weather changes everywhere. And it's a different pattern in La Nina where the opposite happens and the clouds get shifted further west. But in each case, you end up shifting the circulation cell, the energy transport, and then ultimately the weather that occurs globally. One of the really interesting things that often isn't discussed is there are quite a lot of these different types of oscillations that can be local over certain basins or global in their nature, like ENSO. But one of the things that isn't talked about is why ENSO is predictable. And it's ultimately due to what you can see in the top right, these Rossby signals and Kelvin signals. So these are effectively types of slow-moving wave that when they get initiated, they travel quite slowly across the ocean. They reflect off coastlines and then reflect backwards one way, north and south in other ways. But the time it takes them to cross the ocean and come back again actually is the length of time for the El Nino conditions to reset. So it's like a year and a half for one thing to actually reset, and actually ends up with a cycle that ends up between being 5 to 7 years to go from an ENSO to a La Nina back to neutral and then ENSO La Nina. And there can be random variability in this, but once an El Nino starts, it usually is reinforced by these waves. And so that's why it ends up becoming one of the few months and beyond long-term signals that we actually can predict with confidence in the climate. Most other things are actually quite unpredictable and quite chaotic, but El Nino, La Nina, they are stable over months. And so this gives us confidence when we're actually looking to forecast hurricanes, say for the season ahead. If we know a strong El Nino is forming and it's already a place that it's being reinforced by these waves, then we know that we can look at statistics for those years to actually make these predictions. Before I do jump down the hurricane side, though, it's important for, I think, as insurers to know, well, what actually is, given that I've just talked about both east to west impacts, but actually then north to south impacts as well, potentially across all the circulation cells, what actually happens. And I think one of the things we rarely see in the media is what is actually happening in terms of, are there lower risk regions when El Nino occurs? We'll obviously hear the headlines about what is going up in terms of risk. So we see higher bushfire, wildfire in Australia, slightly higher cyclone risk in the Northwest Pacific, and then some really severe impacts on crop yields across Latin and South America. But obviously for insurers, one of the most interesting pieces of this is that we get lower hurricane risk, generally lower severe convective storm risk, and lower at least wildfire weather risk in the US, and obviously biggest market for us. Obviously, the research team over there did a great job of summarizing this at a high level to see where things go up, where things go down. And we've linked that in the back of the pack as well, if anybody wants to take a look. But it is a very neat way of just trying to see, okay, well, if the whole circulation system is changing as a result of this oscillation, where are the places that increase? Where are the places that decrease? With respect to North Atlantic hurricanes, and this is where I guess you can take the information forward and apply in future years, right? The biggest thing that does happen during an El Nino is when that Walker circulation gets shift along the equator. What happens over the Atlantic is that generally we end up in a situation where we increase wind shear. Low wind shear is largely a foundational necessity for a hurricane to form. So wind shear, effectively, it can be defined as the change in wind speed or direction with height. So you can either have wind that increases in intensity as you get higher, which is shown in the bottom left plot there, or it could be that the wind changes direction at height. Either one of those is a high wind shear environment, and ultimately what happens then is the top of a hurricane, if it's forming, will usually get sheared off the bottom of a hurricane. And even very intense storms, when they enter regions of high wind shear, will get torn apart by this. If instead you had very uniform wind speeds throughout the whole of the weather forming part of the atmosphere, you would end up with the hurricane just moving along with the wind and being able to intensify. So during El Nino years, wind shear increases. Conversely, during La Nina years, wind shear generally decreases. And that's why we get more hurricanes in La Nina years and fewer in El Nino years. There are some other background things. One of the other things that does happen, but is more debated in the scientific literature, is that one of the subsiding cells of the Walker circulation sits over the Pacific, over the Atlantic a bit more after it's shifted in the Pacific. And that leads to subsiding air, obviously leads to anti-convection. And so you don't really have the ability to get intense convection, which you need. This is effectively a convergent sign showing convergence and then air rising and creating the atmosphere, the environment for a hurricane to form. Ultimately, with the Walker circulation shifts, you more often get the downward arrows falling over some of the main development regions of the Atlantic. This is a more contentious point, though. It's really the wind shear that is more well known. And the bottom right, when you sort of play that out together, this is what tends to happen. So on the x-axis, this is actually a plot that was shown in the WTW seasonal prediction webinar, but it was about the nicest plot I've seen of this, just to communicate the very simple idea that if we've got named storm count, so number of tropical storms or greater in terms of intensity in the Atlantic basin in any given season, and then you've got the Nino anomaly. So anywhere that's red is into El Nino phase, and anywhere that's blue is into La Nina. You basically see that there are fewer named storms in El Nino years generally, and more in La Nina. And so you can, while there's a lot of variability around that, which I will come to in a few slides' time, it is certainly one of the complicating factors when we're thinking through application of this. You see the general trend, right, downward from El Nino to La Nina. Ultimately, a lot of people look at that and say, well, that is a shift in the overall rate of the hazard in the basin, and therefore potentially our view of risk should shift when we know these El Nino or La Nina events are occurring. So that's some of the backdrop of why ENSO impacts seasonal forecasts for hurricanes. And here, I would really recommend anybody that doesn't know it to go to had a hand in creating this, but obviously my old team at AXA have taken it on. But it's a really nice collaboration between one of the leading centers worldwide of seasonal hurricane forecasts, so Colorado State University, partnering with a supercomputing center in Barcelona. to basically aggregate all of the different centers, forecasts worldwide, and then put them out. And effectively, just so you can quickly see through this, largely between this orange dotted line and the red one is considered roughly normal activity. There's about 7 hurricanes per season in recent climatology on average in the basin. You can see most of the forecasts fall below the average. There's a couple that are around normal activity levels. That's 268 WX and NCSU, I can see. ECMWF also fall roughly in ECMWF for the European Centre Forecasting Centre. But there are no forecasts that actually jump into that, very active season. So no forecasts at the moment calling for a very active season. Ultimately, Colorado State actually recently, just in the last few days, have said that actually given some increasing in vertical wind shear they see, obviously related to the El Nino that I've just talked about, they've even decreased their forecast further for this season. So it's quite an interesting one to then think through, right? We've got these as the forecast base, but what are we supposed to do with that, if anything? Now, before anybody sort of makes a reaction to this, like I know one of the most complicated, I think, decision-making aspects that falls out of this is I've seen a lot of people in La Nina years when there's a massive increase. Let's say if I jump back maybe to this previous slide, when a lot of the forecasts are in that red zone because there's expected to be more hurricanes. I've seen people effectively jump to recommending we should buy more reinsurance. There's more hurricanes here, but I haven't necessarily seen a commensurate encouragement during El Nino years for people to to actually increase cover, increase their exposure, cut rates, whatever, however you wanted to respond to the fact that potentially the baseline is lower. It's quite an interesting um, just split ultimately. But if I was trying to look at this, I would call it a bias. And I think it's a bias driven by a sociological thing to try and protect people. But one of the interesting things, if you haven't seen it, wrote a blog on this, is I think it ends up with people probably being less protected than they could be if people aren't thinking about that bias. But one for another day, I would say that this complicating factors piece actually, to me, makes me second guess the use of this seasonal information at all. And if you're going to use it, you really have to think hard about why and where you can, and the communication around that. The first one I would say is that firstly, I just said to you that roughly 7 hurricanes make appearances in a season. It's roughly between around 6 and 8 that the scientific community would call normal activity. But what is normal, right? We are in a non-stationary climate. We have warming happening all the time and continuing. So what I'm showing here are landfall rates for different regions across the US coastline from a stochastic event set that is produced by Imperial College. They produce a few different versions of this set, but they have a baseline view, which is sort of a long-term average view. And then they've got different climate scenario views. So here I've loaded in a baseline versus the +2.5 degrees C one. And you see actually that the 2.5 degrees C world one is, depending where you are in the southeast, plus somewhere 10 to 25% up on the baseline. But in the northeast, it starts bumping up 25, 50%. I would also just caution, by the way, don't run with this. This is an old version of the Imperial College set, and there's more nuance in it now and a bit of variation. So run with it at your peril. But all it's really here to say is, how do we define what's normal? And then how do we know that anybody that's putting forecasts out, that says something like, oh, it's going to be above normal, below normal, is the same normal as us? It's a really challenging thing to do to make sure that you're reacting in the right way. Have you on level to whatever the forecast center is saying about the seasonal information. Now, to make that even more difficult, this is new work that hasn't yet been published, but again by Imperial. This is Professor Ralph Toomey. One thing he's showing here is it looks again like a bit of a complex plot, but ultimately the red line in the middle, let's ignore the green lines. These are effectively the uncertainty lines. But if I just describe the red line in the middle, This ultimately is the 30-year correlation for what the ENSO phase is actually doing in terms of what its impact to activity in the basin is, depending on the year. So what we're seeing is effectively, if you have an ENSO signal that's positive, you are decreasing the hurricanes in the basin, and they are negatively correlated. That's how it's saying. So and it looks quite significant, right? That it's a minus zero point 0.6 correlation. The uncertainty bounds are all in the negative direction, but this statistically significant negative correlation exists only really after 1980 to present. If we look at the period from 1940 roughly to 1980, actually this El Nino narrative. So when there's a warm or a warm El Nino, then you get fewer hurricanes. This sort of it drops away. And so there's now questions being asked in the academic community. Does what we think we know about El Nino and its impact on Atlantic hurricanes actually exist? If it does exist, why does it exist now? Why has it existed for 40 years? Why did it not exist in the period roughly between 1940 and 1980? And then why did it exist again in the period 1900 to 1940? So there's some really complicating factors that all to me just increases the uncertainty in the information that's being passed about the ENSO forecasts. And then the final complicating factor is, if it wasn't enough, is these two effectively we all, for good reason, like to look at analogies in the insurance industry and look to like to look at similar years, right? So we ultimately here have analogous years of very strong or strong El Nino events. I've called them super El Nino events. So the 2015 season, strong El Nino, very strong El Nino, um, was as we expect, below average hurricanes, roughly average named storms, so tropical storm strength and above, but below average ACE. So ACE is a measure of both frequency and intensity. So roughly below average overall aligns with our narrative. But the other very recent strong El Nino we've seen in our history was 2023. In that one, we had the actual bang on average 7 hurricanes in the basin, but in terms of named storms, we had 20 of them. There's 11, 10 or 11 roughly in a normal season, as is talked about by the hurricane community at the moment, and we had double that, fourth most active ever. So there's this other complicating factor that, okay, while the average is there, the any random year can be not just out by a little bit, but really well out. And what does that do to you, the information that you're trying to use? All of those things, I think, should feed into a decision maker if they are going to respond to the climate information that exists from El Nino. So there's some key questions that fall out of that for me. The first one is, as risk takers, how should we respond to a system in which we're confident there's been a shift in the baseline? So I'm saying ultimately there that we know there's an El Nino, and we are confident that it's going to be there, and we are confident that on average there's a shift in the risk. Um, well, we have at least some confidence probably after some of those complicating factors. The second piece, can reinsurers shift core views of risk on timescales less than a year is a key complicating factor actually from the more business side of things. But then what do the complicating factors when you bring them all in, what do they actually do to the information in a seasonal forecast? The final one is really where we're going to try and drive at for the rest of this presentation, though. How can a decision maker evidence that the decision they've made was the right one, given the balance of evidence at the time? And I think this was always something that the underwriters I used to work with, I always felt that this was the real challenge, that there could be seasons where they had backup covers where the rates would pricing, of the backup cover was doubled compared to what the model rate might be, going well beyond what any seasonal forecast would be. But if that backup rate got hit for a second time in that ultimately in the season, that underwriter, that company just looks a bit stupid, probably ends up being a sore thumb. And being able to talk about, well, actually, no, it went wrong. but actually it was still the right decision given the information I had and the price we were ultimately getting. I felt that was always the challenge that we were trying to overcome. And that's ultimately how we're proposing to find a way through this uncertain information. It falls into, as I mentioned very early on in this, something that's known in decision making and decision theory as the confidence approach. Now, this, as I said, is a real challenge to try and give an overview for coherently in about 5 or 10 minutes. So what I'm going to propose to do is I'm going to give you the very high level what the confidence approach is and what the core components are. And then that's effectively me thinking, okay, let's take the theory and present that to you very lightly. What Giacomo, I think, is then going to do with his underwriting hat on is actually flip this into an underwriter's shoes. Okay, now how do we take the information that exists with an underwriter and flow it back into the confidence approach? And hopefully we get to a point where you guys can then think about picking that up and applying in your own world. So with me on the theoretical side and starting here, on the left-hand side, what we've got is first you need to start with uncertain information. Now, we can do this in a number of ways. If you have a single model vendor, you can start breaking out what you think about uncertainty around the models. If you've got multiple model vendors, you can start, banding them and using the different predictions for different aspects of risk. I'm going to take the complication of the full cat models out of this, though, and let's simplify the sort of overall view. So on the very left-hand side, I've got a projection of risk, say, for hurricane impact in Florida. And ultimately, what I'm seeing here is I might have 50 models that I've made up for predicting that impact. Now, what you see of the bands above each one of those is me saying, in fact, I'm going to simplify that. It's 30 models. So I'm going to say I'm going to take I'm going to take a best estimate that might be what the market price is. It might be what I think the best model is, but that is ultimately the dot on the line 0 to 1. Then I'm going to take the 10 models around that best estimate, then the next 10, then the next 10. So ultimately, we are grading up. And basically, what it's saying is if you only need low confidence in a decision, maybe you only want to load your best estimate with the nearest 10 models. But if you need medium confidence, maybe you should expand your uncertainty band out to capture more of the models. And if it's actually, a very big decision, then maybe you should expand it out further. And obviously, by doing this, you can start to think about comparisons about relative risk between different modeling types. So hurricanes might be relatively narrow compared to earthquake models for Pakistan, as an example. But always what we're trying to do with the confidence approach is not make sure we capture the uncertain information around the risk itself, but actually capture two very important things. Firstly, what's at stake, and ultimately, what your types of decision will be. And I'll talk about this slightly more on the next slide. And then ultimately what your appetite for risk is and whether you are risk seeking or risk averse, really. And mapping those three things together actually ends up with a story that you can tell that actually it always shows that we are making good, confident decisions, even if it goes wrong, given all the information at hand. So this is ultimately, if we take the uncertain information being the prediction of El Nino and its impact on hurricanes and what the hurricane rate changes to, that sits over on one side. We need to elicit stakes on the one hand and cautiousness on the other. So on the left-hand side, you've got effectively how significant is this decision. In philosophical research, I hear most people saying something like, oh, it's on the 0 side, it's like £1, you buy a lottery ticket. So it really doesn't matter to you if it goes right or wrong. On the opposite side of the scale, at 1, that means you're getting shot if you get it wrong. I've tried to translate that through here to insurance, right? It might just be that 0 is going to be an immaterial, completely not going to feel it, not going to even see it, like loss of profit if this decision goes wrong. But on the other hand, if it goes wrong, maybe you go insolvent at 1. So you have this sliding scale, and for every decision, you would sort of land it on this scale. On the cautiousness side, it ultimately becomes what appetite do you actually have for volatility, and how often are you happy for it to go wrong? Now, if you're a risk-seeking reinsurer, some of them I've worked with in the past, actually you have quite an appetite for volatility and you're happy for it to go wrong because actually that's where you find profit margin often in your business plan. But if you're risk averse, you're a big direct insurer with big portfolios of very predictable risks, maybe you don't want it to go wrong. And ultimately, where you end up getting to this, I think a really key piece of the confidence approach is that you will end up with different answers for the same risks based on your stakes cautiousness and how you're treating the uncertain information. This is very core, I think, to how this flows through. But as I said, I think it can be applied to any risk. It doesn't just have to be forecast information, it's anything uncertain. But what's interesting, I think, about the using it for forecast information is for the first time you can start to justify where and when you're going to use forecast information and actually communicate why you might not. Obviously, this can be therefore used for El Nino, La Nina. It can be used for climate information if you want to trigger that. But I think in this instance, one of the things that me and Giacomo were thinking through is with so many complicating factors with El Nino, we find it very difficult to jump to decisions that will very easily be triggered given all of the uncertainty that exists around ENSO forecasts and its impact on hurricane. So what we've decided to do is try to take the idea and instead of looking at forward seasonal prediction, look at some forward weather information where you've got narrower uncertainty and more constrained uncertainty. So I'm going to pass over to Giacomo, where he will effectively give you that background. But I think one of the things I would say immediately off the bat before I pass to him is it's important to note weather isn't climate, right? So climate is largely known as the average state of weather. But weather models generally are much more physics-based. The errors and biases and the uncertainty overall is much better constrained. And therefore, I think it's a much nicer, neater use case to use that forward-looking in-season information to change decisions. And it could be decisions about anything. So with that, I'm going to pass over to Giacomo to give that sort of underwriting lens example.
Amazing. Thank you, Tom. Yeah, let's go to the next slide. So yeah, now we're gonna go through an example of like a realistic scenario, which I lived in my previous employment a few times where I was there. So we do have like, let's say, a storm forming out at sea. We might know that it might grow to a hurricane wind intensity level. But there's still plenty of uncertainty around where it might land. So immediately, very likely, management we start asking, for numbers like what is our exposure in the area, how much we might be facing in potential losses, but also things like, what is our share in the market there compared to our competitors? Are we more exposed than others? And so on. Let's say that we can answer to these questions. Once we do that, so what do we do with that? It would be very useful to extend to this information to answer other questions like do we keep binding in the exposed region, or do we buy live cat protection, or simply can we help our clients prepare for the events? Hopefully, you hope that if I do prepare, that might help lower potential losses. So normally, so if we move to the next slide, Tom, thanks. So normally, the tools that are available are, the actual public forecasts that are published. However, they tend to answer questions like where is the storm most likely to go and what is the best estimate around the intensity. Many of you might have the idea of the NOAA cone of uncertainty, where you only have like one track and a cone that shows the statistical error in the past 5 years. So it's really not capturing the information that is pertinent to just that storm, that is capturing all of these historical storms that happened in the basin, in that area, in the past. So the information there is a bit, it's useful for public service, but not really useful for underwriting decisions. The other way is that you can use catastrophe models. However, catastrophe models are catered towards, they're calibrated towards giving you annual figures. So, what is your cat loss is going to cost you for the year. So none of these tools really fit into what is in reality the underwriting question, which is usually what does this particular storm mean for my exposure right now, not in a year, and how can I make decisions despite the level of uncertainty that is present in the forecast. So we do have uncertainty around where the storm might land, and we also have uncertainty around what the wind speeds might be. So you see in that picture there, that's an historical forecast for Hurricane Milton. In red, you might be able to see a track that is like the best estimate for the control member. In the light blue, you have IB tracks where actually the storm went. So, and all of the other lines in white are all of the other possible scenarios coming out of the ensemble members from the forecast. So you can see that immediately, the first question from the business, do we have a number? First of all, it shouldn't be a number. It should be many. You should be looking at distributions of numbers. How can you do that? So, and how can we answer to the underwriting question? We can do that together with both the live information when it comes out from the live forecast, as well as the historical data on live forecasts that are present in the scientific catalogs. Please, Tom, next. So, yeah, how can we use the live forecast to guide underwriting decisions and provide better insight on risk exposure? So let's look at what we have available. So we have the information coming out from the forecast tracks, and that is the uncertain information. So we can use that to work out what are the probabilities of strike and probabilities of specific triggers that might breached. So for example, we can take the forecast track and use them as use every single ensemble member from the forecast as a single scenario, and you overlay your portfolio of whatever is your exposure. It could be a geographical region, it could be a parametric structure or a single site, doesn't really matter, that's your stake. And then you intersect the two and you start looking what is your distribution of values, and that is what is your stake. Whatever is your metric of choice, it could be a simple gross TIV aggregation, maybe potentially way better if you take into account the deductibles and the limits and the reinsurance layers, so you can work out a meaningful exposed values. You can also use internal know-how from your engineering team or literature to work out what might be a potential loss for each of these locations, depending on the likely wind speeds that are going to be affecting them. And you can work out what your potential losses might be. So those are your stakes. And then you have your level of consciousness. So as Tom said, essentially, what is your risk appetite? If I have all this information, what do I need to take an informed decision that I'm confident with? So let's say that for me, I want to buy live cat protection. That would trigger when I have a certain amount of exposed values, but also when I see a certain level of agreement between the ensemble members. So you see that distribution. So on the right-hand side, you have your very worst case scenarios, which might be still of interest for you to understand and understand what what potentially what accounts might be affected by that, or if you look more at the center of the bell distribution, what is the level of agreement there from your scenarios along potentially unexpected loss. So can we combine this consciousness and stake together? Definitely. We can confidently structure all of this into a decision framework to trigger some actions. Tom? So is the information coming from the live events enough for this? Potentially, but information from historical events is also available for these forecasts. So like the plot that you saw before, that's an historical event. That's a storm that happened a couple of years ago. But what we can do is we can replay past storms as they were seen at the time, so not how they ended, and then we can figure out a number of things. So first of all, can we trust the information that is coming out from the forecast? So in the graph here, you have a plot of the positional error between the forecast from ECNWF and IB tracks, and you can see that the error is growing by the lead time hour, which makes sense. We are more confident of knowing the weather forecast if we are 1 day away from now rather than 5 days away from now. But that might help you to understand at which point you don't trust the forecast anymore, at which point the uncertainty is just too big compared to your risk appetite. How much do you want to gamble when you take a decision? So things like this, information coming from the historical forecast might be helpful to find out what your triggers are, but also it might be useful for you to figure out, to relive scenarios and run simulations and to answer questions like, would this parametric structure have paid out, or would we have bought live cat protection in this case? Yes or not? Should we or should we have not? Also, would our binding rules have saved us money for this event, or cost us some premium maybe? So the historical archive is what makes the live feed trustworthy, and it quantifies how much confidence each lead time deserves and where my company's risk appetite aligns.
One thing, I'll jump. Can I jump? There's an extra thing there as well, because as you can probably tell, Giacomo's been on the underwriting side, and so is thinking about this a lot. One of the things I also saw was there was a lot of questions around senior leaders just wondering when they should pick the phone up for the client, right? At what point do we actually just want to call them and warn them and let them know we're there and potentially help advise them. I think these types of things can also be structured into this confidence approach. It doesn't have to be that specific business decision either, so it can handle any type of decision. The final thing there is just I appreciate what we've dropped on everybody is definitely different to what people would have presented on seasonal forecasts. We have an open tool for playing this through. Basically, it exists completely free. We're just trying to get feedback on the ideas really, and we know it's a big research area across philosophy and decision theory research departments around the world. And so we have been working with London School of Economics and the Light Hill Risk Network to put this together. So this is a few iterations along. We've done previous ones with RIASC as well. So thanks to them for their help. But really, it's trying to combine all of the different types of information you get on seasonal sides and collapse what Giacomo's been talking about, cautiousness and stakes, into the same framework and allow you to structure a decision-making process that you can defend if anything goes wrong. Beyond that as well, I would say we have these resources that we've mentioned. So we'll circulate the slides afterwards, but obviously great work from Inigo to put together what they did. Our confidence approach, perhaps a side climate platform if anybody wants to see some historical archives. But yeah, and other links as well. So please just use them to your liking. Otherwise, thanks a lot for listening. I appreciate everybody being here, and I'll pass back to May.
Thank you so much, Tom and Giacomo. Fantastic presentation. We do have a couple of questions. We've got some time for those. If anyone has any further questions, please do put them in the Q&A and we will address those where we have time. I'll start with the first one. Where do you see underwriting decisions changing over the next few years as more live climate and weather information becomes available?
Yeah, so I've been trying to think about that one a huge amount. I probably go on for another hour about this. I'll try and be really, really tight, and maybe I also appreciate probably Giacomo's got a lot to say. But like one of the things, May, that I was trying to work on the most, I was around at AXA XL when Hurricane Maria hit the Caribbean, and saw effectively decisions not being able to be made because of the way insurance contracts were written, that we had to get loss adjusters there before triggering the payouts and all of that. But we knew with high confidence, given the forecasts we saw at the time, didn't have a framework like the confidence approach, but did lead me to directly to that. But we knew days out, 5 days out, I would say, that we knew a major hurricane was going to be happening in that region. And just being able to trigger certain things, right? It could be partial payouts. It could be just a call to say you probably want to protect yourselves, want to do things, want to be aware that this is happening. Having processes in place, basically, to do things. Giacomo was talking about parametric things. I could see a large appetite for taking big indemnity products that exist across a lot of the North American basin, and actually trying to hybridize them out to sort of partial parametric, and that scale up to full indemnity, but hybridize them by using live event information, forecast information, and then yeah, things that are happening on the ground. So you're always helping your client, and probably at the end point as well, reducing the ultimate payout by allowing some mitigation actions to occur prior to the event by releasing funds early. So I'd like to see that type of thing. I know there's a lot of underwriters I talk to now trying to think through the same thing. Maybe give to Giacomo for his quick response. Oh, you're on mute, Jack.
Sorry, I was on mute. Yeah, no, I agree with everything you said, Tom. And I think that also the availability of all of these new data feeds that didn't really exist up until 10 or 15 years ago will push the market to change and to adapt.
Great, thank you. Another question. Does the confidence approach fit alongside CAP models, or is it meant to replace part of that process?
It definitely can fit alongside them. I think it is a complicated picture, and it's one I've been trying to think about a lot. So where I would see it is that you'd be trying to fill out the uncertainty space. Now, the really complicated piece of this is, what do you do with a single model, and what do you do with multiple models and their structural differences? In the simplest instance, all I would be saying is, if you take my prior example of that, I had a best estimate for hurricane risk and 10 models to go for the low confidence bound, and then 20 for the medium and 30 for the high bound. What I would say is, I would always be an advocate of trying to structure different views of risk. So potentially using different structural models for one, but actually stressing assumptions about models for another. So maybe I can give it an example. On Verisk have just released a new hurricane model with different climate signals that are contained in the event set. And you could actually start subsetting out different event sets for different narratives that it might exist around the climate signals. And from that single Verisk model, create a few different ones. So at that point, you've actually taken a single model, made it a suite of uncertain information, and it's that would be the core feed into the confidence approach. So I would see confidence approach fundamentally just layering in with catastrophe models, but it is going to take some thought from users to figure out what the exact flow of information is there.
Great, thank you. Someone else has asked, if El Nino is meant to suppress hurricanes, why have we still seen some pretty active seasons?
So that's ultimately the chaos that exists in the system, and this is the big complicating factor. I think that while generally, I think it's that thing that the averages happen. So on average, you'll get more wind shear, but in random single years, those narratives just won't hold all the time. And so on average, you'll get it, but there will still be big years. So it's effectively a bit like you're just weighting your dice in some sense a little bit lower, but you still have the potential for extremes. And I think it is a crucial question for understanding properly because it feeds into the confidence approach in terms of what's your appetite for volatility. Because if the mean rate goes down, but you still are so cautious and don't want volatility, then it doesn't really change much because you still have the propensity in El Nino years to get very extreme seasons.
I think we have time for maybe one or two more questions. One question here is, are you saying we should actually be changing our view of risk this year or just being aware of the forecasts?
That's the decision that I'm not going to make for anyone. And depending on where I was at, I would say yes, you should, and no, you shouldn't. And it comes down to how happy you are to be wrong. I think it's the cautiousness layer of the confidence approach. If you're extremely happy to be wrong, and you don't mind being a sore thumb if it does go wrong, I would say there's probably enough information in the mean of the ENSO forecasts to change your view of risk. But if you're not happy to be wrong, then you shouldn't change. And ultimately, yeah, that's what you'd have to elicit from yourself. Yeah.
Thank you. And kind of following on from the question about the confidence approach, how is the confidence approach different from just using expert judgment?
So it's largely I would say it structures non-expert judgment actually. So you could use, on the one hand, you could build uncertain information from catastrophe models, which you might call objective, or you could build uncertain information from doing an expert elicitation of different experts in the field. All the confidence approach does is keep that information existing in the chain until you've put your attitudes and appetites for risk down. So really, it's just a way of making sure you've utilized an appropriate level of information, whether it comes from expert elicitation or modeling or anything else.
Great. Thank you so much, Tom. Thank you so much, Giacomo. Amazing presentation. Thank you to all the attendees for joining as well. As I mentioned, the session has been recorded, and we will be sharing the session along with you. And Tom, I think you confirmed that we will be sharing slides as well. Maximum Information also have some resources that they'd like to share with you, so we will be circulating those following the webinar as well, as long as information about CPD accreditation. Thank you very much again, Tom, Giacomo, and everyone who has attended.
Thanks for having us.
Thank you.
Thanks, guys.